The sun is the engine of our planet. It gives us light. It provides the energy for all life, but our world is getting hotter. The balance has been disturbed. Our atmosphere now traps too much of the sun's heat. We see the effects everywhere. Heat waves are growing longer and more intense. Glaciers and polar ice are melting at an alarming rate. Farmers struggle as droughts parch their lands. Our cities, filled with concrete and asphalt, become dangerous heat islands. We are facing a global challenge. We need innovative tools to manage this new reality. We need to find ways to cool our planet, especially in the most vulnerable places. We must continue to reduce our greenhouse gas emissions. That is the root of the problem. But even if we stop all emissions today, the excess heat already trapped in the system will remain for a long time. The planet will continue to warm. So, what are these solar shields? Think of them as small, lightweight mirrors floating in space. An artist's rendering of a swarm of many small, hexagonal solar shields floating in orbit above the Earth. A close-up of one thin shield drifting in orbit. They are not one single giant structure that casts a permanent shadow over the entire planet. Instead, the plan envisions a large fleet. Instead, the plan envisions a swarm. Instead, the plan envisions many smaller, independent shields. Each shield would be a thin sheet of highly reflective material. Its job is incredibly simple. Intercept a tiny amount of incoming sunlight. Reflect that sunlight back into the deep cold of space. When a shield is positioned correctly, it prevents that specific beam of sunlight from reaching Earth's surface and atmosphere. Less sunlight, less energy, less heat. The effect is immediate. When sunlight is blocked, the area below begins to cool. It's the same principle as standing in the shade of a tree on a hot summer day. A solar shield does the same, but from hundreds or thousands of kilometers above the ground. By deploying many shields together, we could create a larger but still controlled area of cooling. We could target specific regions that are experiencing extreme heat. The key, the system is dynamic. Shields could be moved, re-angled, deactivated as needed. These are not heavy, rigid structures like the mirrors on a telescope. They would be incredibly light and flexible, more like a sheet of foil, not like a pane of glass. This is essential for launching them into space affordably, and for moving them around once they are in orbit. To build these solar shields, we need special materials. They must be incredibly lightweight, highly reflective, and durable enough to survive the harsh environment of space. The lighter the material, the cheaper it is to launch into orbit. The more reflective it is, the more effective it is at its job of cooling. Durability is key. Micrometeoroids and intense solar radiation are relentless. Scientists are exploring several promising candidates, from existing materials to lab-stage options. Each has its own strengths and weaknesses, so the final choice depends on cost, performance, and manufacturability. A familiar material that could work is Mylar. You might know it from shiny birthday balloons or emergency space blankets. Mylar is a polyester film that can be made incredibly thin and coated with aluminum to become highly reflective. It's well understood and relatively inexpensive to produce. Aluminum-coated polymers are a similar, slightly stronger, longer-lasting option. These are already used in satellites and other spacecraft, so we understand their behavior in space. They offer a practical, off-the-shelf starting point for first-generation shields. Looking ahead, scientists are excited about graphene. Graphene is a single layer of carbon atoms in a honeycomb lattice. It is the thinnest known material yet among the strongest. A graphene sheet is almost transparent, but can be engineered to be highly reflective. A fleet of solar shields would be useless without a brain to control it. That brain would be a network of smart satellites and powerful artificial intelligence systems. Satellites sending Earth observation data to a central AI hub, then commands going to a swarm of solar shields. We cannot simply park the shields in space and hope they are in the right place at the right time. We need a system that can constantly monitor the Earth, identify areas in need of cooling, and direct the shields with incredible precision. This requires a constant stream of data and the ability to make complex decisions in near real time. The mission begins not with the shields, but with the satellites that watch over our planet. These satellites are our eyes in the sky. They would be equipped with a suite of advanced sensors. Infrared cameras would map surface temperatures, allowing them to spot heat waves as they form. Spectrometers would measure atmospheric composition, tracking clouds, tracking dust, tracking pollution, which all affect how much sunlight reaches the ground. High-resolution optical cameras would provide visual context. All this data would be beamed down to ground stations or processed directly on the satellites themselves. This creates a living, constantly updated map of Earth's thermal state, a global weather report focused on heat. This is where artificial intelligence comes in. The sheer volume of data from these satellites would be overwhelming for human analysts to process quickly. AI algorithms, however, can sift through this information in seconds. They can be trained to recognize the telltale signs of a developing heat wave or to identify a glacier that is melting unusually fast. The AI would not just spot these hotspots. It would also predict how they might evolve over the next few hours or days. It could run thousands of simulations to determine the most effective way to deploy the shields to mitigate the threat. The AI's role is to turn raw data into an actionable plan. It would decide which specific region needs cooling, how much cooling is required, and for how long. It would then calculate the optimal position and orientation for each shield in the fleet to achieve that goal. These instructions would then be transmitted to the shields themselves. This decision-making loop, from sensing a problem to devising a solution, needs to be incredibly fast and reliable. The AI acts as the central nervous system for the entire solar shield network, ensuring that the fleet acts as a single, intelligent, and coordinated entity. So yeah, that's the idea. Once we have the shields and the AI to control them, we face a critical question. Where do we put them? The location of the shields in space, their orbit, has a huge impact on how they can be used. Different orbits offer different advantages and disadvantages. Coverage, speed, energy requirements. There is no single perfect location. The ideal solution will likely involve placing shields in several different orbits to create a versatile, multi-layered system. Engineers are primarily considering three key regions: low Earth orbit, geostationary orbit, the Lagrange points. LEO is about 200 to 2,000 kilometers above Earth. Satellites and LEO can circle the planet in as little as 90 minutes. LEO shields could shade many different locations over the course of a day. That makes them good for short-term, mobile emergencies like heat waves that move across a continent. But a single LEO shield can only cool one spot for a few minutes at a time. Continuous cooling would need a constant stream of shields passing over the target area. Section 6. A single shield in space can do very little. The power of this idea comes from coordinating a massive swarm. They must move and work together like a flock of birds, like a school of fish. This is where the concept of butterfly flight comes in. Butterfly flight: flaps, tilts, glides. Similarly, each shield must make tiny, precise adjustments to position and angle. When thousands do this in unison, the swarm can shift its focus, change its shape, redirect its cooling effect with grace and precision. Orchestrated by the system's AI, the shields are active. Each needs a way to move. Some could have tiny, highly efficient thrusters, miniature ion engines. Those engines use electricity, likely from small solar panels, to expel ions and produce a gentle, continuous push, allowing slow orbital changes over hours or days. Other designs use sunlight pressure. Solar sails, large reflective surfaces catching solar photons like a sailboat catches wind. By changing sail angle, shields can be nudged without fuel. Coordination is the complex part. The AI won't command every shield individually. It issues general instructions. Move to cover this specific area. Reduce shading by 10%. Shields then talk to neighbors to compute local moves. Each shield knows its position relative to others to avoid collisions. This decentralized, flock-like behavior adds resilience. If some fail, the rest compensate automatically. Imagine a heat wave over a coastal city. The AI detects it. It commands the swarm to focus cooling on that city. Shields in loose formation begin to adjust. Each one tilts slightly using thrusters, using sails, Like thousands of butterflies flapping in sync, they alter their paths. Over hours, the swarm coalesces. Its collective shadow falls over the target city. As the heat wave passes, the AI issues a new command and the swarm disperses to standby formation. This is coordinated, butterfly-like flight in space. Section 7. For a solar shield system to be useful, it must be fast. When a deadly heat wave strikes, we need a response in hours, not weeks. The speed of the system can be broken down into 4 key stages: sensing, deciding, moving, cooling. Understanding the timeline for each stage is crucial to evaluating feasibility and effectiveness. The total response time, from first sign to relief on the ground, depends on the technology and orbit of the shields. In an ideal scenario, the system could react with surprising swiftness. The first stage is sensing. This is the job of the satellite network. Modern sensors can detect changes in surface temperature almost instantly. The limiting factor is how often a satellite passes over a given area. With a large constellation of observation satellites, we could achieve near-continuous global coverage. This means a new hotspot could be detected within minutes to a few hours of its formation. The data would be relayed to the AI, triggering the next stage of the process. This part of the system can be very fast, providing an early warning that lets the rest prepare. The second stage is deciding. Once the AI receives the data, it must analyze the situation and formulate a plan. This is the fastest part of the entire process. A powerful AI on dedicated computers can process vast amounts of information in seconds or minutes. It can weigh different factors such as cloud cover, wind patterns, population density. The decision to act can be made almost instantaneously once the problem is identified. The third stage is moving the shields. This is the slowest and most challenging part of the timeline. The time to reposition depends heavily on orbit and propulsion. Shields in low Earth orbit are already moving quickly, so it might be a matter of waiting for the right part of the swarm to pass over the target, which could take a few hours. For shields in higher orbits, or for major repositioning maneuvers, it could take hours to days. Finally, there is the cooling effect itself. As soon as a shield moves into position and blocks sunlight, cooling on the ground begins immediately. The air temperature in the shaded area can start to drop within minutes to hours. The ground itself will take longer to cool, but immediate relief from direct solar radiation is significant. While days or weeks are needed to change larger weather patterns or cool the ocean, the system can provide rapid, localized relief from extreme heat. This speed is what could make solar shields a life-saving tool in a warming world. Section 8. A solar shield system offers tantalizing benefits, but it also comes with significant risks and opens up a great deal of uncharted territory. We must weigh the potential rewards against the potential dangers with great care.